Okay, in this lesson we're going to talk about finding roots for polynomials, the remainder theorem, the factor theorem, the rational zeros theorem, and upper and lower bounds of the roots of a polynomial function. Okay, we had some audio issues earlier when we originally recorded this, so yeah, we're gonna see what we can do. So first off, at the top, what you don't see is the remainder theorem, which says if a polynomial is divided by x minus c, then the remainder is the same as the function value f of c. Okay, so we've got that example 1. It says use the remainder theorem to find the remainder. We're given that 2x cubed minus 3x squared plus x divided by x minus 1. So this says if we plug in that 1 into our that first polynomial, which will normally be our function f, and we get 0 out, then the factor theorem says that that's a root or a 0. The remainder theorem says if you get anything else, then that's the remainder. Okay, so if you get whatever you get when you plug in that c value, then that's the remainder after you divide by that binomial. Okay, so the factor theorem just said if you do that division of a polynomial by x minus c and you get 0 as your remainder, then of course the 0 remainder means that that is a factor of the function, and that means that that c value is a root or a 0 or an x-intercept. Okay, there's example number 2. You can look at, jot that down. So next up, we've got the rational zeros theorem. The rational zeros theorem says to let f of x be a polynomial function with integral coefficients, the only possible rational zeros of f of x are p over q, where p is a divisor of the constant term and q is a divisor of the leading coefficient. So you've got your polynomial in standard form. Think of the constant term, which is the term at the end, being associated with p, and the leading coefficient being associated with q. So example 3 says f of x equals 6x cubed plus 5x squared minus 21x plus 10. All right, so it's got an order of 3, so we're looking for 3 total roots. They could be rational, they could be irrational, they could even be imaginary. But we're going to see which ones we can find. The rational zeros theorem will show us possible rational zeros. And then if we need to find irrational after that, we can do so in another method. So we take our p-value. So 10 is that constant at the end. So possible values of p are all the divisors or factors of 10, positive and negative. So we've got 1, 2, 5, and 10, plus and minus. Those are our possible p's. Our possible q's come from our leading coefficient, which is at 6. So factors of 6 are 1, 2, 3, and 6, plus or minus each one. So now those aren't our possible rational roots, but we're going to use those to find them. So p over q is going to give us our possible rational roots. Now here's the fun part. We've got to pair up each of those p's with each of those q's. So under C, we've got them organized positive and negative, because we're going to have a positive and a negative of each value. So one method is to start with your first p, so positive 1, and then use each of your q's as the denominator. So we get 1, 1/2, 1/3, 1/6. Then go to your next p, which is 2, and you get 2, 2/3, 2 over 2, which is already 1. We've already got that, so 2/3 2/6, and then go to your 5, and so on. Okay, and you got your positives and your negatives. In this example, it asks for you next to graph the function on your calculator, so graph f of x, and then approximate on your graph which of those possible roots that we just found is it going to be. Okay, so those p over q's. Okay, so on our graph, it looked like we had a root at like -2.5, which was -5/2, close to 1, and then 1. That close to 1 was 2/3. So those 3 intercepts of our graph show us the 3 roots: x equals 1, x equals -5/2, and x equals 2/3. So we can test those using the factor theorem to see if those are indeed roots. So using synthetic division, we can divide x minus 1 into our original function. That was kind of cut off a little bit on the video there, but you can see got the 1 on the outside, our function's coefficients on the inside, and then we do get 0 as our remainder. So 1 is a factor. -5/2, same thing. Notice that we can now divide -5/2 into what we got as our answer to the synthetic division from the previous one, because it's got to be a factor of that new simplified function. Okay, so again, we get 0 for that. We're left with 6x minus 4. That's a linear function, so we can just solve that for x. We get -2/3, so that proves that -2/3 is also a 0. All right, so next up, we're going to talk about upper and lower bounds. So now this is different from the bound above and below that we talked about in Unit 1. This is talking about the bounds for where your roots are going to be. So this is kind of a domain horizontal issue. So in our graph here, we've got A is a lower bound. So that means that there are going to be no roots to the left of A, or smaller than A. B is our upper bound, so no roots are going to be to the right of B, or greater than B. Okay, so this is for a given function. So upper and lower bound tests for real zeros. If f is a polynomial function with the degree bigger than or at least 1, with a positive leading coefficient. Let's suppose f of x is divided by x minus k using synthetic division. If k is bigger than 0 and every number in the last line is non-negative, then k is an upper bound for all real zeros of f. In other words, if we're testing a number bigger than 0 and we do our synthetic division and everything on that bottom line is non-negative, in other words positive or 0, then that is an upper bound. There's going to be no roots bigger than that number. Okay, to test for a lower bound, if the number is less than or equal to 0, and we do our synthetic division, that last row has to alternate non-negative and non-positive for it to be a lower bound. Okay, so let's look at this example. We want to prove all real zeros of f of x must lie on the interval -2 to 5. Okay, so that -2 is going to be our lower bound, or we're going to test it to see if it's a lower bound, and we're going to test the 5 to see if it's an upper bound. All right, so using synthetic division again, let's use -2 as our c value, or k value in this case. Work through the synthetic division, and notice we start off with a positive, then go to a negative, then a positive, then a negative, then a positive. So those alternating signs, and then 0 is okay in there as well, shows us that negative 2 is a lower bound. So we're not going to have any roots in this function less than negative 2. All right, so go ahead and in your notes, you test to see if 5 is an upper bound. Okay. So, next example. We're going to find all real zeros of that function f of x. So if we find our p's and our q's, which come from our constant and our leading coefficient, then we've got 1, 2, 4, and 8 for our p's, positive and negative. 1 and 2, positive and negative for our q's. So if we combine those p over q's, then we've got 1, 1/2, 2, 4, and 8. But since we've already found the lower bound is negative 2, then we can cross out that negative 4, because that's outside or less than our lower bound, and the negative 8. And you've already found that 5 is the upper bound, so we can cross out that positive 8. So now we're left with 1, 2, 3, 4, 5, 6, 7 possible rational roots. Okay, so see, finding the upper and lower bound could narrow down our possible roots significantly. In this case, it cut out 3 of our possible roots. So let's go ahead and do synthetic division. Let's find the remaining ones. In cases like this, you can just kind of pick and choose. If you want to do it systematically, you can work left to right, or if you have a hunch on what one might be, then just try that one. So let's start with 1. See if 1 is a rational root. So we do our synthetic division, and we end up with a remainder of 9. So no, 1 is not a root. So let's go on to, let's pick the next whole number. Whole numbers are usually easier to do synthetic division with. So let's try 2. Doing our synthetic division. Our remainder turns out to be negative 20, so 2 is not a root either. All right, let's try our other positive whole number. Let's try 4. And if you'd like a refresher on dividing polynomials, there's a link on the right column of the Unit 2 page to some Khan Academy videos. There's also some good review in your textbooks. Just look for dividing polynomials or synthetic division in the index. All right, so 4. We get a remainder of 0. So 4 is one of our roots. Yay! So we found one root. Awesome. So now, let's see. What are we going to do next? Okay, and now remember, when we find one of our roots, we can use that bottom row to do our synthetic division with from now on. So that 2, 1, negative 4, negative 2, in a sense, we factored out x minus 4 from our original function. But with that new function, 2, 1, negative 4, negative 2, any of our roots that go into that function must also go into our original. So it's kind of when you find one root, your synthetic division gets simpler and simpler with each root that you find. Okay, so negative 1/2 we try next, and it turns out that negative 1/2 is also a rational root. So what we're left with, again, that bottom line that was kind of cut off in the video, bottom line 2, 0, negative 4, if we put in our variables, is 2x squared minus 4. So that's a quadratic. We don't need to do synthetic division with a quadratic. You can solve that by hand. So add 4 to both sides, divide by 2, square root both sides. Don't forget your plus and your minus when you square root both sides of an equation. So we found all our rational roots using synthetic division. In this case, we did it by hand to find our irrational roots, positive and negative square root of 2. Okay, so that's 1, 2, 3, 4. Those are all of our roots. So the degree of this function was 4. We found 4 roots. So now we want to write out our function in factored form. So we get f of x equals x minus 4 times 2x plus 1. That comes from our negative 1/2. X minus root 2 and x plus root 2.